Assalamu alaikum, dear students. Hopefully you are well and good and must be catching up with the lectures on time. Today we are going to indulge with the most important topic of this chapter, very conceptual but very easy topic. Dear students, today we would be studying the life cycle of a process, that what steps or phases are involved from the creation, execution till the termination of a process. We would study that a process goes through certain steps in order to finally get executed by the CPU, by the processor. A common life cycle of a process involves 5 steps, such as new state, ready state, running state, blocked, also called as waiting state, and terminated state. A process goes through all of these stages in order to finally reach to the termination stage, in order to get converted into an output. But if we take an extensive overview of this life cycle of a process, it has 9 or 10 stages, such as new state, ready suspended state, then running state, running to ready state, running to waiting or blocked state, running to terminated state, then waiting or blocked state, then waiting to ready state, waiting to suspended state, terminated state, etc. If you successfully absorb the concepts of a conceptual topic, it becomes really easy for you to attempt these kind of questions. My belief is that conceptual topics are basically more charming than the non-conceptual ones. They increase your analytical and critical thinking skills. Dear students, as a part of check and balance process, your knowledge level and memorization would be tested through an online time-based test. It would allow you to take a keen interest in the topics by viewing the material repetitively, by asking relevant queries, etc. This test would be conducted, inshallah, after Eid. You would be informed about the dates afterwards. Before moving towards the actual topic, before discussing the life cycle of a process, you need to understand that what is actually a program, because a process stems from a program. Because a program, when gets loaded into the main memory RAM, it becomes a process then at that time. Program is an executable file containing the set of instructions written to perform a specific job on your computer. This is actually a definition which belongs to a software, as we say that a software is a set of instructions. Likewise, a software can be called as a program. So a program is a set of instructions. Any software or program has certain options or instructions present by default inside it. Suppose a user is using MS Excel software to perform calculations. So as per this diagram right now displayed in front of your eyes, that software or program can have multiple options or instructions inside it in order to facilitate the user to perform different tasks. Likewise, MS Word is an executable file containing the set of instructions which helps us to create, edit, and print the electronic text files. So, when we apply different options of a software or a program on our data, different processes are created. Clicking an option or applying an option on the data creates a new process. If you apply 6 options on the data, that means you are creating 6 different processes. Multiple processes can belong to a single program. As I've said earlier, that a program can contain multiple instructions or multiple options inside it. So multiple processes due to these multiple instructions can belong to a single program, to a single software. as one program has multiple options inside it. These softwares or programs are not permanently stored on the primary memory or inside the main memory RAM in your computer. These softwares or programs, along with their instructions, are actually permanently stored on a hard disk on a secondary memory device inside your computer. Now, if you have grabbed the concept of a program, now let's move towards what is actually a process. Processes are the abstraction of running programs. A program is a part of a process is a part of a program under execution, as instructions or options are a part of a program. Process is an executing instance of a program. For example, when you double click on some software, suppose MS Word software icon on your computer, when you open the interface of a program or a software, a process gets started then and there that will run the notepad program or suppose MS Word program. As you can see in this diagram, a process further has threads inside it. You can say that threads are invisible instructions running in the background or running on the background of a software. Suppose when I said that when you double click on some software, suppose MS Word software, that software opens up, its interface opens up. So you haven't clicked any option for running that blank page or for running that interface, but an invisible thread or an invisible instruction automatically charged up, and it just displayed that interface or page in front of your eyes. So a process contains one or more threads. Threads are the unit of execution in process. Threads are the smallest unit of execution schedulable by an operating system. In single threaded processes, the process contains one thread. In multi-threaded processes, the process contains more than one thread. There's more than one thing going on. A thread is a part of the process itself. Threads are like different rooms in one building, means different threads in one process, and different buildings for one company means different processes for one company. It is so much easier for different people in one building to just work together, as they have easy access to each other and that building's resources. So a program can have multiple processes, and a process can have multiple threads inside it for execution. Means multiple threads belong to one process, and multiple processes belong to one program or to one software. Now let's have a glimpse of the process's life cycle. So the first state of the life cycle of a process is new state. As you can see in this diagram, new means a created stage. Names can be different for different stages. So in new state or in created state, suppose you want to open MS Excel software, you want to open MS Excel program. As you already know, all softwares, programs and files are permanently stored in your computer's hard disk. Hard disk is a secondary storage device. So when you would click that MS Excel software, operating system would fetch that MS Excel software from the secondary memory hard disk and temporarily loads that MS Excel software into the main memory RAM. Now MS Excel program has entered the new state of a life cycle of a process. Actually, when some program is stored in the secondary memory, and from secondary memory that program wants to get loaded into the RAM, we can say that that program is actually present in the new state. It has not been yet loaded into the RAM, but it wants to get loaded into the RAM. It is for the while it is actually stored in the secondary memory. We can say that that program is actually entered the new state or created state. Now that program has become a process in the new state. The MS Excel program, which is picked up from the secondary memory and loaded into the main memory RAM by the operating system, is called as a new process. When operating system fetches a program MS Excel from the secondary memory in order to get it loaded into the RAM, at that time that program MS Excel actually became a process. The next stage is ready stage or ready state. Whenever a process is created, the time when operating system actually fetched that MS Excel software or program from the secondary memory hard disk, at that time operating system made it a process. So when it enters the ready state, operating system fetches that program, making it a process. Then afterwards operating system loads it into the ready state. Whenever a process is created or a program is loaded into the RAM, it directly enters in the ready state, in which it waits for the CPU to be assigned. The operating system picks the MS Excel program from the hard disk, loads it into the main memory RAM. The processes which are loaded or reside in the main memory RAM are ready for the execution, are called as ready state processes. Of course, when operating system fetches a program from the secondary memory, makes it a process, then loads it into the RAM, we say that when operating system loads a process into the RAM, we say that that process has entered the ready state. And that is very obvious why any process enters the RAM, why any process enters the ready state. Answer is that in order to get executed by the CPU. So there can be many processes present in the ready state at the same time. If you are using multiple options of MS Excel one by one, every option actually creates a new process. So ready state, after loading the program into RAM by the operating system, we can say that a process has been created for that program in RAM. That created process is now present in the ready state. The process is ready for its execution inside the ready state. After the creation of a process, the process enters the ready state, that is, the process is loaded into the main memory RAM. The process here is ready to run and is waiting to get the CPU time for its execution. Processes that are ready for execution are placed in a waiting queue or priority queue inside the RAM. Of course, when there are multiple processes present inside the RAM and all these processes are waiting for the CPU to get them executed, actually operating system at that time inside that ready state creates a waiting queue. You can call it as a ready queue, a waiting list, and it arranges all these processes inside that waiting queue or inside that ready queue. There can be multiple processes present in the ready state inside the RAM, and all these processes would be placed inside a ready queue inside the ready state. Now the third state, you can see this diagram displayed on the screen. The third state after created or new state after ready state is a running state. One of the processes from the ready state will be chosen by the operating system for the execution from that ready queue. If a system has only one CPU, then it would execute only one process at a time. Then the other processes afterwards would be executed. If a system has multiple processes, then it can execute multiple processes simultaneously. If that system or computer has multiple processors or CPUs, multiple processes would be executed by multiple CPUs at the same time. Amongst the processes present in the ready state, the CPU chooses only one process amongst them. The process will now be executed by the CPU and it is in the running state. The process is chosen by the CPU for execution, and the instructions within the process are executed by the CPU. A process which is getting executed by the CPU is actually present in the running state. As you can see in this diagram, from the ready state, the process goes to the running state. Actually, operating system assigns a process from its waiting queue, from its ready queue, to the CPU for execution, or you can say that CPU fetches or grabs a process from the ready queue, from the waiting queue of the RAM for execution, and when that CPU applies an instruction on that process or executes that process, we called it as running state of that process. When that process is getting executed, we say that that process is present in the running state when it is getting executed by the CPU. Then the fourth state, which you can see on your screen, is block or wait state. You can see that purple colored block where it is written as waiting. You can call it as waiting state, you can call it as blocked state. From the running state, a process can go to the waiting or block state, or a process can make the transition to the block or wait state. Why? During execution of a process in a running state, as we earlier said that CPU starts executing a process. But during execution of a process in running state, when that process suddenly needs an input-output operation, or that process suddenly needs another instruction, that process wants another instruction to be applied on it. That process wants to apply another instruction on its data. That process then waits for a certain resource to be assigned, or waits for the input from the user. The operating system moves that process from the running state to the block or wait state for that purpose. CPU leaves the execution of that process as the operating system sends that process to the waiting state, as well as operating system assigns the CPU to the other process in the waiting queue in ready state, because now the CPU is available. Of course, when CPU was executing a process in the running state, suddenly that process actually wanted another instruction, another input by the user to get applied on it. So at that time, operating system just stops or halts its execution, and operating system CPU halts its execution, and CPU just, or operating system just sends that process to the waiting or blocked state, so that process can attend any input or output operation from the user. Afterwards, the fifth and last basic state of a process's life cycle is completion or termination stage. As you can see on the screen, that is the red block which shows the terminated state. When a process is transferred from the ready state to the running state for running or executing the process, and if that process does not get transferred by the operating system to the waiting or block state, then the CPU successfully executes that process by applying its associated instruction on it in the running state. When the process finishes its execution, it comes from here, from running state, it comes to the termination stage, or to the termination state. We can say that in termination stage, the process has now been killed, the process has now been executed, so it just finishes then and there. It just gets terminated by the operating system in that terminated state here. So in short, a program, we can say that a program gets fetched from the secondary memory by the operating system in new state. In this new state, you can suppose that operating system was fetching a software or a program from the secondary memory. So that was happening in the new state when the program or software was being fetched. When that operating system was fetching that software or program in that new state, it actually became then and there it came into the new state. It became a process. So that program, when gets loaded into the memory, into the main memory RAM, it becomes comes in the ready state. It gets placed into the waiting queue in the ready state. In the ready state, when a process comes, actually it gets placed into the ready queue or waiting queue inside the RAM in ready state. Afterwards, operating system sends it to the running state, here in the running state, for execution by the CPU. If that execution gets interrupted by some input-output operation, then the operating system sends that process to the waiting queue or blocked to the waiting state or blocked state for providing input-output resources, or in order to provide input-output devices. However, if there is no interruption occurs in the running state and CPU successfully performs the execution or the running of that process, and that process does not get interrupted by any input-output operation, the process gets executed by the CPU completely, and after successful execution, the process is afterwards sent to the termination stage in order to get terminated as the output has now been generated. Now, if we talk about further it, that processor or CPU executes only one process at a time. As we already discussed, that a process has various states. These states include whether the process has executed or whether the process is in waiting state, waiting for some input and output operation from the user, or whether the process is waiting for the CPU to run that program or process. So CPU will divide its time among many processes. Those are ready for execution. When a process changes its state from one state to another, this is called as the process state transition. For example, a ready process goes into a running state. A running process can go into a waiting state. A running process can go to the terminated state. So a process passes through different states. These stages may differ in different operating systems. The various states of the process are as follows. In general, a process can have one of the following 5 states at a time, such as new state or ready state or waiting state or running state or terminated state. But here in this extensive study of the life cycle of a process, we would explore some other states too, along with these basic 5 states. Now we are taking an extensive overview of some other states too, along with these basic states. So again, starting from the new state, that a process is said to be in new state when a program present in the secondary memory is initiated for execution, or it is fetched by the operating system for the execution. Operating system fetches that program from the secondary memory and loads it into the RAM. New state is actually the initial state when a process is first created. So this new state is actually the initial or a beginning state when a user requests for a service, or when a user requests for a program or software from the operating system. Then the operating system will initialize that program by fetching it from the secondary memory. We will say that the operating system will initialize actually, or will create a process here in this new state. As you can see in this diagram, that a process is created in the new state, and from the new state it is then transferred, you can see that, From the new state, the process is being transferred to the ready state by the operating system. Then a ready state. A process moves from new state to the ready state after it is loaded into the main memory RAM. When some process comes inside the RAM with the help of operating system, as soon as it enters the ready state, we say that now it has to be placed in the waiting queue. It has to be placed in the ready queue of that ready state inside the RAM. So a process moves from new state to the ready state after it is loaded into the main memory and is ready for execution. Many processes may be present inside the RAM at the same time. The operating system arranges all those processes in the ready queue or waiting queue. In ready state, the process waits for the CPU to become available. If some process is coming inside the RAM, the only purpose is that that process is waiting inside that RAM for the CPU to become available. So the process is waiting to be assigned to a processor. Ready processes are waiting to have the processor, are waiting to have the CPU allocated to them by the operating system so that they can run or get executed by that CPU. When the process is ready to execute, when the process is ready to get executed by the CPU, but the process is waiting here in the ready state, the process is waiting for the CPU to execute them. So then this is called as the ready state. So the queued processes are ready for the execution, waiting for the CPU to become available inside the ready state. Now, after the new state, after the ready state, in this extensive study of life cycle of a process, the third state is ready suspended state. Actually, the processes from the ready state get transferred by the operating system into the suspended ready state as they were initially present in the ready state. We are talking about the processes as they were initially present in the ready state inside the main memory RAM. But why they got out from the ready state? Because of lack of memory space inside the RAM. Lack of memory space inside the RAM actually forces these processes to get suspended. That's why these processes are placed inside this ready suspended state. Operating system sends these suspended processes from the ready state to the ready suspended state, and that ready suspended state actually exists inside the secondary memory. Remember that new state starts from the secondary memory. New state actually is present inside the secondary memory, as well as ready suspended state also is present inside the secondary memory, while the ready state is present inside the RAM. So we say that's why these processes again get placed into the secondary memory. In fact, the processes in ready suspended state are present inside the secondary memory. You can see this concept in this diagram clearly. That is your new state, which is present inside the secondary memory, from where process actually got inside the ready state with the help of operating system. Here the process was waiting for the CPU to get available, but suddenly the process came to know that there is lack of space inside the memory, inside the RAM. So the operating system actually suspended that process, and the operating system actually transferred that process from the ready state to the ready suspended state. So we can say that a process moves from ready state to ready suspended state if a process, if some other process with higher priority comes, or if some process with higher priority has to be executed but the main memory is full. So the operating system creates the space in RAM by throwing that lower priority process out of the ready state, and operating system sends that lower priority process into the ready suspended state. The process, that low priority process, remains in the ready suspended state until the RAM becomes available. When main memory RAM becomes available, the process, that low priority process, is brought back to the ready state by the operating system. Here you can see that operating system actually transferred that low priority process to the ready suspended state. When the RAM became available, or it got empty, or it has some space, operating system transfers that low priority process back to the ready state for execution, and it places that low priority process again inside the waiting queue. We can state this concept like that: process that was initially in the ready state, the process was actually placed in the ready state but was swapped out of the main memory, and placed onto the external storage or secondary memory by the operating system, is said to be in the suspended ready state or ready suspended state. The process will transition back to the ready state whenever the main memory RAM space becomes available. There can be more than one process in the ready state, but due to memory constraint, due to memory limitation, if the memory is full, then some processes from the ready state they actually get placed into the ready suspended state. So when it is time to select a process to run or execute, the operating system selects one of the processes from the ready queue and moves the process from the ready state to the running state. When the process has been assigned to a processor by the operating system scheduler, the processor or CPU executes the process by applying its instructions on it. CPU executes a process as per allotted time quantum. You must know this, that when operating system actually fetches any of the programs from the secondary memory and loads those programs into the RAM and into the ready state, and all these processes are waiting inside the ready state, inside the RAM, for the CPU to get available. Of course, these programs these processes are placed inside the waiting queue or inside the ready queue waiting for the CPU. CPU would actually assign them with some time slice or quantum for execution, and CPU just picks up or fetches or grabs one process at a time, then the other process, then another process, and executes all these processes one by one in a sequence according to their allotted time quantum. If CPU has given 7 nanoseconds to a process for execution, it will exactly execute that process for only 9 nanoseconds. After 9 nanoseconds, the process would it can go to some other process for execution. So it means that CPU or processor assigns each process with a time slice or quantum for execution and executes each and every process according to that allotted time quantum. Then in this diagram you can see that when the process is running inside that running state, when the process is running under the CPU, or when the process is getting executed by the CPU in this running state of the life cycle of a process, then this is called as the running state of the process. And when a process is running, then this will also provide some output on the monitor screen. When CPU will execute a process by applying some instructions on it. After its execution, an output would be generated, and that output could be seen on the screen. So we are done with new state, ready suspended state. Then we talked about the fourth state, the running state. After fourth state, running state, we would talk about the terminated or termination state. Once the process finishes its execution in the running state, or it is terminated by the operating system, it is moved from the running state to the terminated state, where it waits to be removed from the main memory. So here in this diagram you can see that this exit states, actually here it means termination or terminated state. After the completion of the process, after the complete execution of the process by the CPU in this running state, the process will be automatically transferred, or it will be sent by the operating system to the terminated state, to the exit state. So this is also called as the termination state of the process. After executing the whole process in the running state, the processor will deallocate the memory which was allocated to the process. So this is called as the terminated process. When after sending that properly executed or properly run process to the termination state, the CPU or the operating system will just deallocate its memory space, or just deallocates the memory space occupied by that process, and it will be sent to the termination state, and output would be generated. Now this is very important state. These are the states involved in the extensive overview of that life cycle of a process. Now the sixth state is running to ready state. Running to ready state means that the process is going from the running state to the ready state. Why a process would go from run state back to the ready state? When the assigned quantum time of a process expires, the operating system sends an interrupt signal to the CPU to stop execution of that process. Operating system shifts that running process back to the ready state. You can say that a process which was actually sent from the ready state to the running state for actually execution, and that process was actually happily getting executed in the running state by the CPU. But the first case can be that when during the execution of that process by the CPU in the running state, the assigned quantum expired, or the assigned quantum time of a process when expires, the operating system in that case sends an interrupt signal to the CPU to stop the execution of that process, as the time slice assigned to that process has been expired. So the CPU stops the execution immediately of that process, and operating system shifts that. You can see that in this diagram. Operating system shifts that process back to the ready state as its quantum or time slice has been expired. That was the first case, that why a process which was being executed by the CPU happily in the running state was that why it was actually transferred back to the ready state. So the first scenario was that actually the time quantum or time slice of that process expires, so the operating system actually transferred that running process back to the ready state. And the second scenario can be that if a high priority process comes into the RAM, the operating system interrupts the execution of the running process in the running state and transfers that low priority running process back from the running state to the ready state, and operating system sends that high priority process from the ready state to the running state on the place of that low priority process, as that low priority process has already been transferred back to the ready state by the operating system. So these can be the two cases that why a running process from the running state is transferred back to the ready state. So the first case is that a running process or a process getting executed by the CPU can be sent back during its execution, can be sent back to the ready state. Number one, if its time quantum has expired. Number two, if a high priority process came, so the low priority process during its execution would be sent out or transferred back to the ready state. Suppose there are two processes, process 1 and process 2. There are two processes present in the ready state inside the waiting queue or ready queue inside the RAM. So the CPU compares the priorities and both of these processes want to get executed by the CPU, and so the CPU compares the priorities of these two processes. For example, process P1 has sent to the running state by the operating system, and the process 1 is now being executed by the processor or CPU. At that time processor process P2 generates, or you can say operating system actually generates an interrupt signal for the processor or CPU. Why the operating system generates an interrupt signal for the CPU? It actually wants the CPU to stop the execution of process number 1. So then the CPU actually compares the priorities of processor P1 and P2 as the operating system has sent the high priority process 2 also to the CPU. As the CPU was already dealing with the process number 1 and the operating system sent another process 2 to the CPU. CPU is now comparing process 1 with the process 2. If process 1 is greater than process 2, then the CPU continues the execution of process number 1. Otherwise, the CPU would switch to the process number 2. If process number 2 has high priority than the process number 1, then the CPU would stop the execution of process number 1. Process number 1 would be transferred back to the ready state by the operating system, and the CPU would start the execution of process number 2. The next state, or the seventh state, is running to waiting or running to blocked state. As in the previous state, we discussed that the process was transferred back to the ready state from the running state during its execution due to two scenarios, due to the scenario of high and low priority. Now the process can also be transferred from the running state to the waiting or blocked state. And why is that so? We will explore it out. So from the running state, a process can make the transition, or a process can be transferred to the block or wait state. Process moves into the waiting state if it needs to wait for a resource, such as waiting for user input or waiting for a file to become available. So when a process is waiting for some input and output operations, or you can most probably say that when a process was getting executed inside the running state by the CPU, but that process suddenly actually needed some input output operation. So when a process is waiting for some input and output operation, then this is present in the waiting or blocked state, and in this state process is not under the execution. Process is only present under the execution, or process is under the execution when it is actually present in the running state. When it needs some input output operation, operating system simply transfers that process from the running state to the waiting or blocked state. During execution of a process in running state, when that process suddenly needs an input-output operation, that process wants to apply another instruction on its data, the process then waits for a certain resource to be assigned or waits for the input from the user, and the operating system transfers that type of process which is actually waiting for some input-output operation to happen. Operating system just simply transfers that type of process from the running state to the waiting or a blocked state. In that waiting or blocked state, that process can wait for the input-output operation for the input-output device to become available, and the event of input-output operation can happen. Here in this diagram, you can see that we were talking about that the process was actually getting executed or running by the CPU here in this running state, but suddenly the process actually needed an input-output operation, needed an input-output device, needed an input-output resource. So the CPU in this running state stopped the execution of that process. Operating system sent that process from the running state to the blocked state. Now, as the process has come inside that blocked or waiting state, here in this state, that process can wait for the input-output operation and can wait for the event to happen. So, whenever the process requests some input-output operation or needs input from the user during its execution, it enters from the running state to the blocked state. The operating system moves that process from the running state to the blocked or waiting state for that purpose. The process continues to wait here in this blocked or main state, inside the main memory RAM, and does not require the CPU or does not require the CPU's execution. CPU just leaves the execution of that process here in this state, and the operating system sends that process to the waiting state, as well as operating system assigns of course, that is obvious that the process has now transferred to the blocked state. Here in a running state, the CPU is now free. So the CPU is now available. So the operating system assigns the CPU to the other process in the waiting queue in the ready state, because now the CPU is free, so it can attend some other process from the ready state. Once the input-output operation of that process waiting in the waiting state, waiting in the blocked state completes, the process was actually waiting for some input-output device, or it was waiting for some input-output event to occur. So when that input-output event occurs, that state completes, the process again goes to the ready state. You need to remember that as the process has now attended its input-output device, and that event has occurred for which that process was waiting, like some input-output operation event, after using some input-output device or after using some resource after the application of input-output operation. Now that process from the blocked state again moves to the ready state. Means that process was coming to the blocked or waiting state just to attend some input-output operation, to attend some resource. After attending that resource, after happening of that event, that operating system, process would just be transferred back to the ready state by the operating system. Another thing we can say that is a process is put into the waiting or blocked state if the process needs an event to occur, or an input-output device is to read that process. The operating system does not provide the input-output or event immediately, then the process is moved to the waiting state by the operating system. Now, another very important state, and the 8th state is that waiting to ready state. Important thing is, we have discussed this point just seconds ago, waiting to ready state. So the process which was transferred to the waiting or blocked state from the running state for using input-output devices for completing some input-output operation, when that process completes that input-output event or operation for which it was waiting inside that waiting or block state, when that event occurs or happens or it completes, that process again moves back to the ready state after performing that operation, gets placed by the operating system inside the waiting queue of ready state and waits for the CPU to execute it. Or we can elaborate this concept as, you can see that from the running state, that process actually shifted back to the waiting or blocked state because the process was actually waiting for some input output event to occur. So once that input output event occurred, and the process attended the resource, or process attended that event, or process attended that input or output, after attending that event or after the happening of that event, the process now moves back from the waiting state to the ready state. Operating system again transfers that process after the completion of that input output event. Operating system transfers that process back to the ready state, and inside that ready state again that process would be placed inside a waiting queue, inside a ready queue, and that process would again wait for the CPU to become available. A process in the blocked state is moved to the ready state by the operating system when the event for which it has been waiting occurs. For example, a process is in a running state, needs an input-output device, then the process is moved to the waiting state or blocked state by the operating system. When the input-output device is provided, that resource is provided by the operating system to that process in that waiting state, the process afterwards moves to the ready state from that waiting or blocked state. Now the ninth extensive stage is of waiting suspended state. Means the process which was actually present in the waiting state got suspended. How? Similar to ready suspended state, a process moves from waiting or blocked state to the suspend state if a process with higher priority has to be executed but the main memory is full. When the waiting queue inside the waiting state becomes full, then some of the processes will be sent to the waiting blocked state or waiting suspended state. Remember that ready state has its own waiting queue, while blocked or waiting state has its own separate waiting queue. But the similarity here between the ready suspended state and waiting suspended state is that when the space was full in RAM, the process was transferred from the RAM to the from the ready state inside the RAM to the ready suspended RAID in that state, just because the memory space was full inside the RAM. Likewise, it happens with the waiting suspended state. When the space is full in the waiting state, the space is full, a process does not get any space, so that process is shifted or transferred from the waiting state to the waiting suspended state, because inside the waiting or blocked state there are too many processes and the memory space inside that waiting or blocked state is not available. So moving a process with a lower priority from wait state to suspend wait state creates a room for higher priority process in the ready state. It means that suppose that there are 2 or 3 processes present in the waiting or blocked state. So the higher priority process would be able to stay inside that waiting or blocked state. But if the memory is full, the lower priority process would be kicked out or would be thrown out of the waiting or blocked state into the waiting suspended state. So after a resource or input output operation becomes available to a process in waiting state, the process after completion of that input output event, that process moves to the suspend ready state. Or when a process moves after the completion of input output event, a process moves to the ready state, the space becomes available. So the another process from the suspend ready state moves back to the waiting or blocked state. When main memory RAM gets some free space or becomes available, that process is then moved to the ready state where it is placed in the queue waiting for the CPU. Means there is no space available in the waiting or blocked state, and there are too many processes. So the high priority processes would get placed inside the waiting or blocked state when they would would get done with their events. Those high priority processes would go to the ready state. So now the space is available in the waiting or blocked state. So the suspended process from the suspended blocked or suspended waiting state goes back to the waiting state. Also it gets done with its input output event. After happening of that event, that process goes to the ready state for finally waiting for the CPU to become available. So the point here to say is that there is a waiting queue inside the waiting or blocked state too. Ready state has its own ready queue or waiting queue, while the waiting state has its own waiting queue. Inside that waiting queue, suppose 5 processes are placed, and the space becomes less, and 5 processes cannot just get the space inside the waiting state at the same time. So what the operating system actually do, what it performs is that it transfers some low priority processes to the suspended blocked state, and it creates room for high priority processes here. Those high priority processes get done with their input output event, and they get back to the ready state for CPU's availability. When that space here becomes available, and as the high priority processes are now transferred to the ready state by the operating system, here the space is now available. So the processes, low priority processes from the suspended blocked state, actually they move back to the waiting state queue. They get done with their input output event, with their input output resources, and after completion of the event, those processes also they get transferred to the ready state. But sometimes it happens that from the suspended state, those processes actually they go to the suspended ready state, and from the suspended ready state they go to the ready state. When some memory space in the RAM becomes available, they move from the suspended ready state to the ready state, where they get placed into the ready queue or waiting queue for the CPU to become available. This is similar. We can say that suspended blocked state or suspended waiting state is similar to the ready suspended state. Means this suspended blocked or suspended waiting state is similar to the ready suspended state. The processes in blocked suspended state or waiting suspended state are actually in the secondary memory. They were initially in the blocked state or waiting state inside the main memory, waiting for some event, but lack of memory actually forced them to get suspended and these processes actually they get placed in the secondary memory suspended blocked state. A process may go from a blocked suspended state to ready suspended state if its work is done, but if its work is not done, it needs to move back to the waiting or blocked state for that input output event to occur. Instead of removing the process from the ready queue, it's better to remove the blocked process which is waiting for some resources in the main memory. So since it is already waiting for some resource to get available here, it is already waiting for some resource to get available. Hence it is better if it waits in the secondary memory and makes room for the higher priority processes inside the waiting state. So these processes complete their execution once the main memory gets available and their wait is finished. Important thing to notice here is that 3 states in the life cycle of a process, like ready state, running state, and blocked or waiting state. These 3 states, ready state, running state, and blocked or waiting state, these 3 states are actually present inside the RAM. Ready state, running state, and waiting or blocked state. These 3 states are present inside the RAM, while the other 3 states like new state, ready suspended state, and waiting or blocked suspended state, these 3 states are actually working inside the secondary memory. So the summary of the whole topic we read today is that a process is basically created in new state. Here you can see that a process is created on the basis of a fetched program from the secondary memory. So a process is created in the new state. After the new state, that process is admitted, or it goes, or it is transferred to the ready state by the operating system. If the ready queue or the waiting queue of the ready state is full, then the process, low priority process, will be shifted to the suspended ready state. So from the already loaded processes in the ready state, the CPU will definitely choose a process for execution, and the process will be executed by the CPU in the running state. So during the execution of the process may need some input output operation to perform, or the process may need some instruction from the input devices or output devices. So the process has to go into the waiting or blocked state. The process would go from the running state to the blocked state with the help of operating system. If the waiting state is, or the blocked state is full, then that process, that low priority process, will be sent to the waiting suspended state or waiting blocked state. From the waiting suspended state, the process can move back to the blocked or waiting state when the memory of the waiting state becomes available. But if the process was already done with its input output operation inside the waiting state, and after the happening of the event, after the completion of input output operation, the process was actually, if placed inside the suspended blocked state, then in that case the process can be moved from the suspended blocked or suspended waiting state to the suspended ready state. When RAM gets some empty space inside it, the process from the ready suspended state can be moved back to the ready state, where that process would be placed inside the waiting queue or the ready queue of that ready state inside the RAM. And inside that ready queue or waiting queue, the process would wait for the CPU to become available. At last, After the complete execution of the process from the running state would go to the terminated state, and the information of the process will be deleted, and the memory allocated to the process for running would be just killed or would just be deleted. So this is the whole life cycle of a process. We talked about its superficial view based on the 5 steps. We talked about its extensive view based on 9 to 10 steps. We talked about its summary. So this is the whole life cycle of a process. We are done with our today's topic. Thank you for your attention. Stay safe, stay healthy, and Allah Hafiz.